Recording, okay. And then we'll keep going from there. So I'm going to launch a poll here in a bit, and I'll give you a minute as usual, and then we'll discuss the answers afterward. Okay, so I'll give you a minute to look at this question, poll in and answer, and then we'll talk about it. Okay, so a couple seconds and then the minute is up. All right. So the question, the chemical driving force, which tends to cause molecules to move in a particular net direction, is a direct result of which of the following? So a lot of responses for C. Let's see what C says, a concentration gradient of the molecules. So that is correct. So C is correct here. So it's basically asking what is the force, or what is responsible for the chemical driving force rather? And we know that that's the concentration gradient. Okay, so the separation of particles having one concentration higher on one side, lower concentration on the other side, and that is the driving force that moves particles to be at equilibrium. Alrighty, let's look at another question. Okay, final couple seconds here. I'll actually give you a couple more seconds. This one had a bit of reading. So I'll give you another 10 seconds to poll and answer in. Okay, so let's close this and see the answers here. Okay, so the question asked, which statement is false regarding the effect of the electrical force, the electrical driving force created by the membrane potential on a solute? So let's actually go through each of the options here. It's asking which of the following statements is incorrect. Okay, we had a lot of response for D, so let's look at the various options. For a solute that is uncharged, the electrical driving force created by the membrane potential is 0. This is a true statement, okay? If there's no charge on the particle, there's no driving force across the membrane, right? Remember, the electrical driving force is based on the charge on the particle. So A is true. B, a membrane potential of -70 will exert a larger electrical driving force on calcium, a divalent ion, than on sodium, a monovalent ion. This is also a true statement, right? If we have two charges, we're gonna have a stronger magnitude of the driving force than if we have one charge, such as sodium, which is a monovalent ion, right? So another true statement, B, Let's see C, an increased, more negative membrane potential will exert a greater electrical driving force inward on a monovalent cation. So it's saying a more negative membrane potential will have a greater electrical force inward on a monovalent cation. So let's kind of break this down here. If it's a cation, it's positively charged, so it wants to get into the cell according to that electrical force. And we're saying if there's a more negative membrane potential, which simply means that the magnitude or the value there is bigger, we will have a stronger or greater electrical driving force. So C is also a correct statement. D, the membrane potential exerts a greater inward directed driving force on anions than on cations. And D is incorrect. The reason D is incorrect is because the anions do not have an inward directed driving force, right? Remember, anions are negatively charged particles or negatively charged ions. They are not trying to get into the cell because the inside of the cell is more negative than the outside. So if we change the direction here, this would be a true statement, but inward is not the correct direction. It's going to be moving outward. If they're anions and cations would want to be moving inward. Okay, so if you happen to get that question wrong, please examine why and make sure that you understand why D is the false statement and all the other statements are correct. Okay, so let's pick up here where we left off on Monday. We were talking about how we determine the overall direction of the electrochemical driving force. So pretty much we said that there are two forces acting on particles to move them across the membrane. We looked at the chemical driving force exclusively. We talked about what determines that. We also looked at the electrical driving force. And then now we began putting them together and trying to determine what the overall movement of the particle would look like. We said that if we identify the direction of each of the forces individually, then we can sort of walk through this algorithm of determining which force is going to be the dominant force and where the overall ECDF is going to favor, okay? And so we said that if the forces are in the same direction, that was nice and easy, straightforward. The overall ECDF would also act in that same direction. But if they were in opposite direction, this is where we had to now compare the membrane potential of the cell at that state, at that time, along with the equilibrium potential of the particle in question. Okay, if it's potassium, sodium, whatever that particle is, we're going to look at the equilibrium potential, we're going to look at the membrane potential of the cell at that time. If the equilibrium potential, so the first scenario here, if the equilibrium potential was greater than the membrane potential in terms of the size of the value of that potential, then the CDF would be the more dominant force. And so the overall ECDF would follow the direction of the chemical driving force. We also said that if they were equal, so if the equilibrium potential was equal to the membrane potential, then everything kind of canceled out, both forces canceled out. The ECDF is 0, the ions are said to be at equilibrium, and so we see no net movement of the particles. And then if the membrane potential was greater than the equilibrium potential, then the opposite of that first scenario is true. And the electrical driving force, which tends to favor the membrane potential, is going to be greater than the chemical driving force. And so the overall movement, or the ECDF, will favor the electrical driving force, okay? So these are the three scenarios that we talked about in terms of if the forces were in opposite direction, how we determine the overall movement of those particles, okay? So, oops, let's clear this off. Okay, so here we're seeing that kind of a better illustration of what that algorithm would look like. So here we have a scenario where the equilibrium potential is -94, the membrane potential is -70, And here we're going to compare the absolute value. So we're not going to look too much at the negative or positive, but really the value or the magnitude of that force, okay? So here we see that the equilibrium potential is a greater value, a stronger force than the membrane potential. And so if that happens, then the overall force is going, the overall ECDF is going to follow the direction of the concentration gradient or the chemical driving force, okay? Because the equilibrium potential is greater than the membrane potential. And so we see a small outward electrochemical, we see a small inward electrical driving force. We see a larger outward chemical driving force. And so the overall electrochemical driving force is smaller because we're actually subtracting the values here, 94 minus 70, but the overall direction will favor the chemical driving force. And so that's going to be outward or moving out of the cell. Alternatively, on the other side here, this is what would happen if the membrane potential is greater than the equilibrium potential. And we can see that reflected down here. The membrane potential is negative 100. The equilibrium potential is negative 94. And so we see a large inward electrical driving force and then a smaller outward chemical driving force. And so because again, we're subtracting the values here, we're going to get a smaller overall electrochemical driving force. Because the electrical driving force was the bigger force to start, the overall ECDF will now favor the inward direction of the electrical driving force.